Hello and welcome to, I think, episode 17. Definitely the show is the 4coder Lexer show. I think we're on episode 17. So either way, whatever episode it is, the next goal is the stuff that I have written down right here. We need to split off end-of-file transitions from the copy of the model we have here. We need to sort those to the top, and then we need to generate all of our transitions. Right? So let's see about doing that. I believe I have, so the model is just sitting right there. So what I want to do is iterate every transition. So that would just be a matter of iterating every state. For each state, we're going to take the list of transitions that state contains, which we can do right here. And then we're going to iterate the transitions that are stored inside that list. Right? Okay, so we're iterating the transitions, and our goal here is we want to look at the conditions of each transition, and if it has an end-of-file transition condition, if it has end-of-file in there, we want to split it out. So essentially what I need to do is I need to think of a way to do this split that makes sense, and I think the way that makes sense is to first construct a condition set that represents the set of things that I want, like that I'm going to use to create cuts. And then whenever I go and see one of these transitions, I look and see if the intersection of my cut set and the condition I'm looking at is non-zero. If it is non-zero, then the non-zero part of the intersection becomes the one part and the subtraction becomes the other part, and I copy the transition to have both cases, right? So that's kind of what I need to do. So up here I'm going to need to construct a condition set. I'll call this the set cut set or something like that. And then I believe I have a constructor for that. Condition set. How do I make a condition set? Subtract, set, intersect. I see. So I give it an input set and a fields set. So SMI condition set is constructed out of the scratch, and that I need like cut inputs and cut fields. So the input set called cut inputs is going to be SMI input set. Somewhere around here I must have, yes, construct EOF. So that'll let me construct the end of file version. Input set, field set cut fields, SMI field set construct. And for that one, I don't want any particular pins. I want the set to include all possible fields combined with the end of file input. Then for each transition, what I'll need to do is look to see if the intersection, so I'll call this as like condition intersection, and I guess the first thing we'll do is for each transition we'll make sure that the kind of condition we're looking at is not a delimiter match condition, but is actually a condition set, right? So I'll look at the condition kind and make sure that it's a condition set. Then I will take the intersection, I don't know, by doing SMI condition set intersect, and to intersect I want to intersect the cut set with the condition set contained right here, right? And then if the condition I get back has a non-zero size. Yeah, if we have a non-zero intersection, then we have work to do. If the intersection is 0, then the transition I'm looking at doesn't have anything to do with the end of file, and so I ignore it. If it's non-zero, then what I'm looking at does have something to do with end of file, and so I'm going to split the transition into two pieces, one that is the intersection and one that is the subtraction. So in order to do that, what I'll need is a new, I'll need to do it this way: set original set equals, I'm going to just do this. We're going to take original, get a copy of it there, original. So we're doing the intersection of cut and original, and if the intersection is non-zero empty, then we need to do the following things. The transition that we already have will change its condition set to say that it points at the condition intersection. Then we're going to need to make a new condition, or a new transition. Like this. The new transition will have the following properties. It will be inserted right after the current transition, so we have to think about how to do that cleanly, I guess. I have the ability to push at the beginning and end of a set easily, but maybe what I should actually do is just put this somewhere else, because we're going to resort it anyway. So push back onto the states. So what I should probably do is this. Whenever I go to do one of these things, I'm going to just go first equals 0, last equals 0, and we're just going to build a new list as we go. Right? So we start with an empty list. We're going to do the more careful type of iteration, and then with each step, so we take the current node, and one way or the other, the first node gets pushed onto the list exactly as it is. So that just happens without even thinking about it. But the new node needs to get pushed on there if it gets created. And then what else has to happen with this thing? Well, its parent state needs to match the state we're in. Its condition kind is going to be transition case kind condition set. Its condition set is going to be condition set subtract original minus the cut set. Oops. There we go. So that's its condition set. Its activation list is going to be copy action list. Right, and its destination state is going to be this guy's destination state. Right, so we create a new transition. It's identical in every way except that it has the conditions that were removed when we took the intersection here. So this part has only end of file parameters, and this part has this transition has everything but the end of file parameters, because here we're subtracting out the cut set, whereas here we're intersecting the cut set. Right? So again, this has end of file only, this one has everything else. And so then the only other thing is, before we actually go and do that, what we should make sure is that the condition int count I guess what we could do is this. We want to do the subtraction. If we do the subtraction and the result we get back is empty, then we don't need this, because that means there's nothing else in the set, and then we don't need this. So maybe we should do the subtraction first and the intersection. Again, we would still need to check that. Okay, so one way or the other we have to do both of them before we know for sure if we're going to do both nodes. So condition sub, condition set, condition sub equals if condition sub dot count is greater than 0. So if the intersection is non-zero, we update this to be the intersection. If the subtraction is non-zero, we create a second node that contains that. So if either one is 0, so if the initial intersection is 0, then we only need one node, and it's the node we already have, because the intersection being 0 means that there are no end of file things, so we just make no modifications. If we do make modifications, that is to say, we check the second thing we do is say, hey, we're making modifications so far because we have a non-zero intersection, but it's possible that the non-zero intersection is actually the full set, and that would be the case if the subtraction is empty. In other words, if the cut set is completely contained in the original set, it's a proper subset, or just a subset of the original set, then when we do the subtract here, okay, flip it around. If the original set is a subset of the cut set, then when we do this we'll get a 0, and that'll indicate that the whole set we had was already focused just on end of file and didn't have any other behaviors. So then we don't need a copy of that transition, right? We only need a copy of the transition when there was both non-end of file behavior and end of file behavior combined into one transition before. And that's what this creates. Okay. So I need to get in the habit of building with this key. Come on. There we go. Condition sub. Condition is not right. It's condition sub. Perfect. Okay, so I create a condition set. It's the condition subtract. Save it there. We're good. The new transition gets on the list, and so finally the only thing left to do is to update the state transitions to look at the newly built list. Right? So this code here does this part, in theory. I want to be able to debug print that. Is that possible? You don't have the ability to print without... Okay. So I need a different way to debug print transitions. And I'll bet you... Yeah, I need to move that up there. Okay. So this goes here, and this goes down here. And then this we need to figure out a way to realign this. So Lexer primary context, what do you contain? You contain, you're going to need an arena. I'm going to call this scratch. You're not to allocate things on there permanently. A token kind set, tokens, and a Lexer model. I'm pretty sure you actually only need the model. We can now... Whoops, you weren't... I didn't mean to request you. Go away. Alright, anywhere where we use context to get to the model, we can just go straight to the model. Alright, so nowhere in there do I actually use context anymore, which is good, because that means now I can come down here and do this like this. Context arena goes into the scratch, context model goes there. How does that look? Come on, come on. Alright. Right, so now you don't need to do that. Now you can just do scratch models, flags, set numbers. Not sure we actually need to do that right now. But if we're going to start doing optimizations, flag, set numbers, I guess I should probably start doing them like this. Lexer model, so that I can make it a little more generic. So then this can go here, right? Cool. So that builds. So the question now is, how does it look? It's printing out states only. Okay, gotta look into this. Debug Print transitions. I must be obliterating the transitions everywhere somehow. How am I obliterating the transitions though? Shouldn't this be guaranteeing that all of the original transition nodes stay in the list? I'm not removing anything from the list. This should just... yeah, this should just be keeping the lists the way they were if nothing else happened. So I'm going to have to look through this code and figure out what I messed up, I guess. Yeah. Let's take a look. I think it's called generator.exe. I think that's the program it outputs. Visual Studio starting up. Visual Studio starting up. Alright. Didn't mean to edit that line. Please undo it. Go ahead and run one line at a time for me. There you go. Jump down to here. Don't care about that. Get into there. There we go. So the cut set contains one node, one input 256, one empty pin list. Garbage. First, last count. So we start looking at the transitions. This state here doesn't have any transitions. Alright, so maybe our copy isn't fully implemented after all. Opt copy model. So when you copy that model, you visit each state. Wait, copy state set. Okay. I see. Right here we make a new transition. We never actually put it onto the new state, do we? So this right here just needs to push onto the new state transitions first, last, the new transition. And we need to increment the count by 1. How does that look? Okay. So now I'm getting this. So there's my end of file, it's separated out, and at the beginning for root, but for other things it was not separated out before. But here we can see it looks like it's separated out the end of file handler, that looks like it's separated out end of file handler, and so on and so on. So what I'm gonna do to make these even easier to determine is when I'm debug printing transitions, when I have the choice to do one of these, all printable, right? Not you. There we go. All printable equals false. If all printable. There we go. So now I can see these EOFs. Yeah. Yep. Yep, okay, so it looks like this has worked. It's successfully taken the EOFs out of everything else. And it's just leaving them sit there. So the next step of the process has to be that once we take out the EOFs, we want to sort them so that the EOFs come first. So in order to do that, how would we do a sort? Well, we could actually build the sort right into this. So this here is split EOFs and insert at beginning, right? But if we did that, we'd be denying the fact that eventually we're going to want a more complicated sort anyway. However, I think for now that that's fine. I mean, we could do a full sort now, but we're only going to be sorting two things. Later we'll have actual stuff to sort, and then we can move this responsibility into that code. There's no point in predicting how the sort wants to be structured based on a situation where we don't actually have a full example of what the sort wants to look like, right? Does that make sense? So I'm going to go ahead and get this to work here for now. So how I would do that is if alright, so the portion that is the end of file is this first one right now. If I swap it around by a couple of things, I could say sub here, and if the subtraction is, so if original cut, if the original minus this cut is greater than 0, then there's something in the original that got cut out. That's confusing. I don't want to change that. But what I can do is I can say, this is the part that does the intersection, right? Alright, so if the intersection is 0, we just keep it as it is, no changes. If it's not 0, we'll push that on the front of the list, and then push the rest of it on the back of the list. So this way we'll put all the end of files right at the beginning, hopefully. End of file, end of file, end of file, end of file, end of file. Yep, that looks like it's working. End of file, 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 end of file. Yeah, it's totally worked. So you can see what we can do now is a little bit nicer than what we had before. When I go to print out the transitions, first I'll start a loop that handles all the end of file transitions, and then outside of that, like when I find the first transition that's not an end of file transition, it can flow into a separate loop that'll consume the rest of the transitions, right? So there we go, sorted, and now we want to generate transition checks. So we don't need to do this anymore. What we now want to do is say, okay, this code here wants to say do a for loop, and the trick is that we're doing a loop over transitions that actually needs to begin out here. So here's the transitions, well, transition list, transitions equals the state's transitions, and then the transitions first goes here. For as long as that is not 0, we can iterate transitions the way we normally would using that pointer. If the transitions, if this transitions condition that kind doesn't equals a condition set, and if that transitions condition set right, so then what we want to do is see if that condition set contains an EOF input. So because it's a union of nodes, that a condition set could technically be multiple nodes, each of which contains the condition, although technically that would kind of be wrong, right? We'd kind of expect that it would merge them all because they're all going to have the same input set, so it should only use one node unless it needs potentially, well, no, because our field set can represent chains of like any field set it needs to, right? The only reason for the nodes to be separate is if the rectangles don't merge, because the field set can represent any field set. So, I mean, it can represent any field set given enough pin lists. So, what we basically want to do is have a thing that's like if condition, well, hold on, I guess it'd be more like opt condition is EOF only. It'd be something like that, right? So we check if a condition is end of file only, and we have two different situations. If it is end of file only, we want to print the handlers for that end of file stuff here. So this is the code, right? We're inside the code here. We're printing out the check that determines if we're at the end of a file. And so right here is where we're going to do whatever the end of file needs to do. So that's where we'll print off for now, not implemented because we haven't implemented any of the stuff that does action handling, right? Eventually what we'll be doing there is we'll be printing out that transition's activation actions here, right? But not yet. So we check the condition. If we get to the point where the next transition we're looking at is either a null pointer or it does not contain an EOF handler, which it should always be this case and never should be this case, but whatever, then we finish printing this off and we go on to doing stuff down here. Now there's something else that has to happen up here that I guess I'm not accounting for, which is each of these doesn't just print off its own not implemented. Each of them actually has to do some flag checks in here still, but we're not quite going to go for that part yet. I'm trying to get each transition printing off, and then I'll go in and do the checks for each transition, and then I'll do the action lists, right? So the rest of the loop looks like this. We take a loop across the remainder of the transition, so this, wherever this landed, it found a transition that didn't have this condition apply, so we break, and then here we resume handling that particular transition. For each possible transition, there's some kind of if that we don't know how to implement. A not implemented goes inside there, like that. Right, there's an if here that we don't know how to do yet. And then finally there's a goto. And the goto is the one thing we can easily get correct right away without having to build up any other major system. So the goto is we look at the destination state, and we're going to be printing out a state label that matches up here. So here is we're printing a label derived from the state that we're trying to print out. So here we're going to print out the label of the state that we're trying to go to. So the state we're trying to go to is the destination state number, right? And for readability, I will do the same thing that I did up there, which is to add in the pretty name and a comment like so. So string expand the destination state's pretty name. Right, so now we need to implement condition is EOF only to move on. So I believe this is the optimization section, yeah. Alright, so we want to look at one of these conditions. Alright, so if the kind of condition we're looking at is a condition set, then if when we look across all of the nodes in the condition set, if we look across all of the inputs in the node, so we're going to grab the input set inputs from there, and then we're going to say, okay, if inputs.count is greater than 1, or inputs.inputs0 does not equal SMI EOF, then result equals false and break, right? Alright, so what happened here? Here we're making the root condition, and then we're going, alright, these are different cases that bring me to, and then they all say label 0. That's weird. Are all of my labels label 0? Yeah, so it doesn't have state numbers set up correctly. That's fine. All that means we have to do is opt states set numbers. Oh, and you take context, huh? Well, you're going to need to take the Lexer model from now on so that we can apply you from the generator. So the point is that after we copy this, we need to do opt states set numbers on this model here. There we go. So now each of these is a dummy space where we will be printing out a different transition. Here's the transition to 24. Here's the transition to 2, 25, 26, 28, 3, 3, 4, 5, 6, 49, 50, 51, 53, etc., etc., right? So the next goal is we need to get this here where it says if true, and the same thing up here. We need to get those to actually do something useful. So let's go and work on that part. So first let's work on this one. So in what situation would anything other than not implemented come out here? Or rather, anything other than just one thing come out here? Well, if we ever had two end-of-file handlers with non-equal, like, two handlers that handle the case of end-of-file, but that have different flags states that they allow to trigger that handler, right? So essentially what we need to do is check to see if the flag checks for a particular condition are met. Now, that means we're going to need to make a thing that essentially works for any flag set, figures out if anything, if we match that flag set, right? How does that work? Well, it relates to our representation of a flag set. We're not just going to iterate literally every possible type of field. Whoops, I should be looking at the field set. We're not going to be looking at every possible state the field can be in and checking it against a list of value. Like, we're not going to have like, okay, every field's allowed, so if the field equals this, if the field equals this, if the field equals this, etc., etc. That's not how it's going to look. The way it's got to look is if the set has no restrictions, that is, if the set allows for all possible fields to work, then we do no check at all. If the set allows for, everything within a particular pin, then we just check that one pin. If it has two pins that are ORed together, we check that one and we do an OR and then put out another one, right? So we have to kind of turn our thing. Remember, this is a list of our field set is a list of these lists. So it's a union of each of these list things, and each of these list things is a list of pins, so it's an intersection of each of those pins, right? So we kind of need to do a several layer construction here that'll turn it into an AND of ORs, no, an OR of ANDs, to find out if we match. Then later on what we can do is find a way to optimize this by saying, hey, is there any way that we can order our checks so that we are doing the minimum number of checks to figure something out? Like, if we have one handler, or if we have three possible handlers, and for two different flags that can have different combinations. So either the first flag can be 0 is one handler, the second handler is the first flag is 1 and the second flag is 0, and the third handler is the first flag is 1 and the second flag is 1. And so those three handlers cover all possible cases. Then what we kind of want is a thing that just does an if-else on the first flag, and then inside the else case, an if-else on the second flag. And so to build out that system would require a little bit more work, and would give us a more optimal output, right? So that's a good idea to have, but it's not what we're going to do right now. Right now what we're going to do is just a little bit more basic. But before we can actually do any of that stuff, what we actually have to do is we have to figure out how the generated code, let me show you what I mean. This generated code here has no way of even talking about the flags yet, right? There's no variables in this code that contain the flags. So what we really need is to start by introducing each of the flags as a state variable here. Now the next question is, do I want to actually use like flags with enum values on them, or do I want to use like a small 1-byte boolean for each one of these things? Again, the easier thing to do is to go with a 1-byte boolean on everything for now, and then we can switch this to being bit ops if we want it to, or if we think that the extra complexity of bit ops doesn't really pay off, we'd never have to. In fact, it might be that the better thing to do, since we're talking about like a set of like 10 flags, it might actually be better not to do that. I'm not sure. I mean, certainly if you have them as each a separate boolean, the downside is that you are using up more space, and potentially each one of them has to get loaded into a register separately, so that if you want to check something, you're always loading something into a register and then checking it. Whereas if it was a bit field, maybe you could keep it loaded in a register and then just mask it, but keep the mask, like an unmasked version of the field around all the time, so that you don't, so that you don't have to what's the word I'm kind of looking for? You keep an unmasked version of the field around so you don't have to load it back into a register. It certainly would also be possible to perform our checks more quickly, right? I was saying how we could do like if-else ifs everywhere and stuff, but if we wanted to, we could just say whenever we go to do a check against a particular flag field, put it another way, maybe the checks still want to be if-else ifs and maybe they don't want to, but certainly we have places where we want to set more than one flag at once, right? And having them in a flag, like a bit field where we can use different enums or together to make our operations, we would be able to basically make a single instruction that clears multiple flags instead of having to do one instruction for each one, right? So I think we're going to go with the option of pushing them all into a flag field with a variable, right? So in order to do that, what we're going to need to do is for each up here, opt states set numbers, opt states set flag, opt flag set flags set numbers model, right? Now what we want is I guess we want like a 32-bit variable for every 32 flags we have, we want one 32-bit variable rounded up, right? So that's what we'll do first, is we'll do number of flag variables equals, and then we want to look at the model. So our model type should contain a set of flags, and our set of flags should contain a count, and then we'll add 31 to that count and divide by 32, just so that we get divide by 32 rounded up instead of rounded down. And that's the number of flag variables we need. So then what we can do is when it comes time to print this stuff out, gen contiguous control flow Lexer, somewhere in here, right here, we start the function up. Before we go any farther than this, what I want to do is create a new like flags field for every one of those that we need, right? So this will become the thing that just prints out the declaration of those variables. I'll put a number on each one and set them all to 0 initially. And the number is I, right? So now I have flags 0, cleared to 0 at first. Okay, before I go any further than that, what I probably want to think about is, am I going to just print these out as hard-coded values, 1, 2, 4, 8, 16, or am I going to make an enum of them with names or something like that? Right now my flags don't have pretty names, so I'm going to say I don't care so much about that part of it, right? What I do want to do is when I set the flag numbers, flags set numbers. Okay, why can't I type today? There it is. Do I want to assign to each one of them the ID for its flag index and this, or do I want to have just a function that gets that? I think I can just do that with a basic function to help me out. So it would be kind of like, I don't know exactly how I want to do it, but why don't I think about it like this. Flag indices, variable index, and then flag number, right? And then what I would have is just a helper function that gives me flag indices from a flag base number. So gen get flag indices. So I don't have to store flag indices directly. I can just say, what's your flag number, and figure it out. So in order to figure out your flag number, or your flag indices, I'll just call this result since it's easier to say and spell. The result.variable index is found by taking the flag number divided by 32, nice and simple. So if you are the 32nd flag, you go on variable index 1, right? Or rather, what I should really do is take flag number -1, because that's not 0 based, I don't think. Right? Maybe it is. Flags set numbers. Okay, flag set numbers is 0 based. And the real question, I guess, is what do I even use a flag number for so far? So far it's just been used for the printing, which is why it's 0 based. Okay. Well, in that case, if it's 0 based, I don't need to do this. And the flag number, no, flag number is not the right word. Variable index, this is like the flag value or something like that. The flag value is what you get when you take, so divide by 32 is the same as right shifting by 5. So we want the 5 lowest, basically, okay, I see what we want. We want the flag number modulo 32. So this gives me the number between 0 and 31 inclusive, and then I bit shift this up by that. So if on the 31st flag, like if I'm flag number 31, then my flag value is 1 bit shifted 31 times, right? And then this is guaranteed to be between 0 and 31. As soon as flag number becomes 32, we will have a variable index of 1 and a flag value of 1. So we'll be using the first flag, the lowest possible flag, on the second variable, right? So now, anytime I want to check a flag, it's just a matter of getting the flag indices and then using them to figure out which variable to look at, and then using the flag value, anding that in to look at the right number, right? Yeah. So if we wanted to do smarter stuff with our flag fields, one thing we would have to deal with is the fact that if we ever had multiple flag fields, we would still have to do a separate operation for each one. So our optimizer would have the job of looking at those flag fields and maybe either resorting the flags to have the most commonly used ones in similar groups. So things that are used together would be grouped together. And then the second thing we would need to do is, even if we did or didn't do that, we would also want a thing that figures out like how, like, okay, for any operation, which flag variables are in play, and sub-optimize each one as a separate single operation that can't be optimized together because they don't affect the same variable, right? So that's all stuff we can pull off if we need to. Gen get flag indices. Gen get flag indices takes flag number. Okay. So when I'm down here and I'm doing my test now, all I have to do is say, all right, if this is the right thing, then we're going to print out the if that finds out if we're in the right place or not, and then we're going to do this. Okay. So here's what this is going to look like. That's going to look like that. That's going to look like that. The condition will go in the middle there, and then if this is not the first, so then we'll also print out an else right here before the if. And then right here we have to print out the logic that turns a field set into a test to see if the current condition of the field set matches that, right? So what I need basically is gen slow field set check. And to do that, what I'm going to need is slow field set check. So gen slow field set check takes what things? It takes the transitions condition and the output file. Is there anything else it needs? I think that's everything it's going to need. So we need a condition set. And the out. Condition slow, where is slow? Condition dot condition set out. And so now here I'm going to call this the condition set and the out. And then what we would have to do is look at the data structure we're iterating and do it correctly. So it's a iteration across nodes in this condition set. For each one of those nodes, we want to look at the field set and whatever we do, we're going to end up printing out some stuff. If the next node is not 0, then we're going to print out I've been sticking to fprintf everywhere, right? Good. We're going to print out an OR sign between them, because the condition nodes are treated as a union of each other, so they're like this. Now, kind of what I'm actually thinking would make sense is to say that we take a field set fields and have a way of printing that out directly, because this here should actually technically not be what's happening down there. Slow field set check. We kind of want a thing that's like assert that the transition condition set count is only 1 in this case, in which case we can grab the one and only condition node. And then we can say that what we're actually doing here is operating on the node's fields directly, rather than this condition set and then take that out, because I don't think that actually made a whole lot of sense when I started thinking about how condition sets want to work for other cases. Plus, this is a field set check. It should operate right on a field set. Okay. So now what we want to do is, this is a field pin list. Pin list equals fields first. So all of these nodes are actually pin lists. And each pin list we want to, alright, the logic I was saying did make sense, but at this level. So if the next thing we see is not going to be a 0, then output an OR sign. Then right here we output open parenthesis, close parenthesis to contain all the logic of this particular pin list. Now, inside a pin list, what we're going to do is we're going to loop again over field pins. And so each of these nodes is actually a pin. And so for a pin, what we do is we say that we expect, now 4coder has this little helper I can use to check if something has a flag without too much fuss. We check to see if something has a flag, and then if the pin has a next pin, then we're going to fprint out an AND, because the pin list is a list of pins which are intersected together. So we want all of them to be true for the case to be correctly handled. And then what we need to do is we need to put in the name of the variable and the value of the variable right here. So the name is, what did we call it? It was like %d something right here. Something %d. Flags %d. So flags %d. And this right here is some, we'll call it, how do I get an unsigned hex? I need to look that up. Let me see what I can do. Google. Come on now. Unsigned hex value. I think maybe unsigned hex is always unsigned, but I'm just double checking how it works. Okay. Yeah, so hexadecimal is assumed unsigned, so that's fine. And then I'll put an OX right there. And finally, we want to figure out the right values to stick in there. So how do I figure out the right values to stick in there? Well, that's where I do one of these things. I get a flag indices back from the flag number. Where do I get the flag number? The flag number can be found by looking at my pin flag number. Right, so the pin has a pointer to the flag, and the flag itself contains its number, right? So I look at the pin flag number, and I get the indices. Now, the indices contain a variable index, which is the number I want for this, and a flag value, which is the number I want for this, right? So that should do it. Is first condition. So let's see. Here we're alright, we're not quite getting what I expect there. Field set check. So it's doing that. It must be saying, okay. So if it's an empty list, right? If pin list count equals 0, then it's always going to be true. The empty list, since it's an empty intersection, is treated as the full set, so it always evaluates to true. Still not it, huh? Why is that? So you're putting that parenthesis out and that parenthesis out, but you're not saying that. Oh. No. Each pin list. You're saying your pin list is non-zero, but you're also not doing anything in here. You sure your pin list isn't 0? I better take a look at this in the debugger, because that's a little confusing. If it's non-zero, then it should be doing a has flag here, which it's not. Right there, we're not seeing a has flag. So it's not running any of this code, but that means it shouldn't that it must not have any pins to print, and yet if it had no pins to print, it should have printed this, right? So something isn't quite right. Let's go over here. You can go away. Okay. What are you doing there? So the count is 0. Oh, I got it backwards. Duh. Okay. If the count is greater than 0, do the loop. If it's not, give me a true. Alright, so now, if true, do this thing. So that's because there is no competing, there is no other thing. There's no question about whether or not to do this. It is correctly printing if true. Now, if we do a good job, we probably want to at some point determine if the chain of checks is going to have a true and optimize it out. Luckily, a C optimizer will basically always get this for us anyway. So we don't necessarily have to, except that it makes our generated code bigger. So it's very low priority, but maybe at some point we don't want to put out trues whenever we could have looked ahead to see that this was coming. The trick is that the process of discovering that this is going to happen is sort of discovered after we've already laid things out in a way that doesn't, like, by the time we've called this, we've already put down an if, and so this check is too late to do this optimization. That optimization would actually have to happen sooner with something that says, hey, what do you recommend, like, my strategy for implementing this condition be? And just, that would have to be the system that determines that the if is not necessary. By the time we are actually calling this thing, the way this is implemented, the way it like fits in, this essentially is expected to generate an expression level like entity into the code that evaluates the true or false based on whether or not the flags work, right? So this is actually the correct thing for it to do, even long term, for this particular call. So there we go. We have that part working. I don't think we actually have any cases where anything besides true shows up, because I don't think we ever care about what case condition we're in when we meet the end of the file. So the end of the file would always just do this one handler that it has. I don't think it ever has any other choice. Yeah. Okay, so the next thing that happens after this is done, or whoops, sorry, after this is done, is we move on to here, and in here I'm just doing an if true again, and here I can actually do some more work. So what we want to do now is figure out how we're going to test the condition, like a full-on condition set that could have any set of features. So our condition sets might just be, does the input lie inside this set of possible inputs, which is a big old like switch case basically, and then does it match the flags for that thing? But then it's also possible that there are more than one thing that allows it to evaluate to true, right? So to actually do the full test is going to be kind of an ongoing source of optimization work for us. But what's something we can do that is basically going to work? Well, if we don't mind printing this handler multiple times for now, we could just do each test, and if it ever succeeds, print out that handler again for that particular node. So that would basically mean one thing we want to do is say that we have like an internal gen go to dest state thing here that lets us pass in a transition and an output, and it prints the go to for that state's destination right there. And that way we can simplify this. Right, go to the transition's destination state. We might also want one that lets us work like this. Go to state, which just skips the transition altogether. And then this here can just be gen go to state, the transition's destination state out, right? Okay, so that gives us some nice little helpers to do stuff with. And then the rest of this is just our placeholder for what will eventually be the action list. And then this here is the thing that isn't actually doing the test to see if we match a condition node. So all we have to do to see if we match a condition node, or a particular condition set, is iterate the condition set. Condition... Well, I'm going to pull the condition set out. Condition set. Condition set, right? Pull out the condition set and grab the first node out of the condition set, right? And we're going to grab the first node. For each node, what we want to do is check to see if we're in the input set. That's going to be fairly expensive, and not expensive to execute necessarily, but expensive to write right now. It's going to take my time personally to write that, and we're getting near the end of an hour, so I want to wrap this episode up. So but instead of fully finishing what this needs to do, I'm just going to have it do the correct flag checks for now. So to make it do the correct flag checks, I'm going to split this into 2 separate prints, and then in the middle, just like we did on the other one, we are going to do a slow check, or a slow field set check. And we can do a slow field set check because we're looking at each node separately. Then the other thing we have to do is when we're chaining these together, each of these is going to print out the same condition handler over and over again. And since they have go-tos, we don't even need else's. So actually, forget what I was going to say. Actually, this doesn't need a go-to. Yeah, okay. This should just have go-to end right here, and then we don't need to bother doing all this stuff to figure out if we need an else or not. So that will be a little bit nicer. See how that looks. So again, most of these just evaluate to true. So there's kind of an argument to be made that maybe we want to actually handle that because it makes the code look weird, but I'm not sure. Most of these will actually not be redundant once we start putting in input checks. It'll start mattering quite a bit which one triggers and which one doesn't. But right now it looks like they always just all trigger, so it kind of looks silly. But we can find cases where it does real stuff. So like for instance right here, it's checking if flag 1 is set on this thing here. And so one thing I didn't do that I should do is I didn't check the parity of the flag check. So what I mean by that is when I do slow field set check, right now it's actually just testing if the pin is 1, but I also want to be able to say if our pin value equals 0. So if the value we're checking is that we don't want this flag to be set, then we actually have to output a not sign first. Right? So not has flag. So here's an example of when it's checking to see if we're doing a string, it's making sure that this does not have that flag, whereas here it's checking to see that it does have that flag. So I'm a little concerned that all of these are giving me a 1 right there. It kind of looks like they all have a flag number of 0, but I think that'll be something worth debugging in the next episode. So, thanks for hanging out with me. For this episode, we're starting to get the ability to print out our flag checks. We need to debug a little bit with it because I'm not sure that it's all correct. And then we need to build our input checks. Once we have them all kind of working, we then need to actually go back through and put in the action listing, and once all of that's in there, we will technically have the first version up and running, and we can test it to see if it's correct. Once we have it running correctly, we'll go back through and optimize a lot of this stuff. Okay? So until next time, thanks for hanging out, and I'll see you guys around. Bye-bye.